So let's start with a really simple question. Or is it? What is time? I mean, it seems obvious, right? We live in it, we feel it ticking by every single moment. But as we're about to find out, the real answer is one of the strangest, most mind-bending stories in the history of science. This quote from St. Augustine, from way back in 400 AD, just nails it, doesn't it? We have this gut feeling, this intuition about what time is. But the second you try to pin it down and actually explain it, it's like trying to grab smoke. And that mystery is exactly what we're going to unpack today.
Okay, so to get our heads around this, let's first travel back to a view that probably feels the most intuitive to all of us. This is the classical idea of time as this great, big, unchanging clock, a concept that was really cemented in science for centuries by the one and only Sir Isaac Newton.
Yeah, for Newton, time was, it was the ultimate constant. He pictured it as this massive cosmic clock ticking away at the exact same pace for you, for me, for someone on the other side of the universe. It was the absolute, unchangeable background where everything else happened.
So, in this Newtonian universe, the rules were pretty clear. Space and time, they were the bedrock of reality, totally rigid and unchanging. A second on Earth was exactly the same as a second on Mars. The only thing that wasn't absolute was speed. How fast you were going always had to be measured relative to something else.
And you know what? This picture, it was beautiful, it was elegant, and it worked for over 200 years. But then, in the late 1800s, scientists stumbled upon a bizarre fact about light, and it started to poke a huge hole in Newton's perfect universe.
This is where things started to get really weird. A physicist named James Clerk Maxwell was working on his famous equations for electricity and magnetism, and his math kept spitting out this one very specific number for the speed of light. But here's the kicker. The equations just said this is the speed. It didn't say the speed relative to what. And in Newton's universe, that was a question you always had to answer.
So, what do you do when your observations don't fit the model? You try to patch the model, and that's exactly what they did. Physicists dusted off an old idea and said, aha, all of space must be filled with this invisible, undetectable substance we'll call the ether. The idea was that light travels at its constant speed relative to this stationary ether. It was a neat little fix, or so they thought.
Okay, so if this ether thing is real, we should be able to detect it, right? As Earth plows through space, there should be a kind of ether wind blowing past us. And that's what the famous Michelson-Morley experiment set out to find. The setup was ingenious. They'd split a beam of light, send the two halves on a race at right angles to each other, and then bring them back together. If there was an ether wind, one beam should be slightly slowed down, and they'd see the delay.
So they ran the experiment, and what did they find? Absolutely nothing. A big fat zero. No matter how they oriented it or what time of year they ran it, the two light beams always finished in a perfect tie. The conclusion was inescapable. There was no ether wind, which meant there was no ether. Physics had a serious problem on its hands.
So the old rules are broken. The patch didn't work. The stage was perfectly set for a total revolution, and the person who led it wasn't some big-shot professor at a fancy university, but a young, unknown clerk working in the Swiss patent office. His name was Albert Einstein.
You can really see how this all built up, right? For centuries, we have Newton's absolute time. Then Maxwell comes along, and his math says light speed is constant. Then the experiment to explain why it's constant fails spectacularly. It was this huge, century-long mystery, just waiting for someone to solve it. And then, in 1905, Einstein did.
And this is the genius of Einstein. He just flipped the whole thing on its head. He said, what if we've got it all backward? What if space and time, the very things we thought were solid and absolute, are actually flexible and relative? And what if the one thing that seemed like it should be relative, the speed of light, is actually the one true, unbreakable constant of the universe?
So he laid down two new rules, two postulates for his new universe. The first one's pretty straightforward. The laws of physics work the same for everybody who's moving at a constant speed. But the second one, that was the game changer. He just declared that the speed of light is the same for everybody. It doesn't matter if you're on a train or standing on the platform. If you both measure the same beam of light, you will get the exact same speed.
And if you accept that second rule, that the speed of light is the one thing that never, ever changes, well, it leads to a conclusion that is just staggering. If light speed can't change to accommodate your motion, then something else has to give. And that something else is time and space themselves.
And that brings us to this incredible idea called time dilation. It means time isn't universal. It's personal. Your time isn't my time. Not exactly. The faster you travel through space, the slower time passes for you compared to someone who's standing still. Your watch is literally ticking slower than theirs.
And before you think this is all just some sci-fi thought experiment, let me tell you, we have proof. Hard experimental proof. We've put super accurate atomic clocks on jets, flown them around the world, and guess what? They came back running just a tiny bit behind the clocks on the ground. We also see it with cosmic particles called muons, which should decay long before they reach us, but because they're going so fast, their personal clocks slow down and they survive the trip. It's real.
So Einstein went even further. He realized that space and time aren't two different things at all. They're woven together into the single four-dimensional fabric he called space-time. And this isn't some boring static backdrop. It's a dynamic, flexible stage that can be stretched, shrunk, and warped by motion and gravity.
And get this, what's one of the biggest consequences of this new, flexible reality? Only the most famous equation in the history of the world, E equals mc squared. It's not some random brilliant insight. It falls directly out of the math of special relativity. It shows this profound, deep connection between energy and mass that you can only find in a universe where time itself is relative. Okay, I know what you might be thinking. Atomic clocks, muons, space-time, this is all fascinating stuff, but what does it have to do with my daily life? Well, it has everything to do with a piece of tech probably in your pocket right now.
Yeah, your GPS, it literally wouldn't work without Einstein. Think about those satellites whizzing around the Earth. They're moving super fast, so special relativity says their clocks slow down by about 7 microseconds every day. But they're also in weaker gravity, where Einstein's other theory, general relativity, says time speeds up by about 45 microseconds a day. Engineers have to constantly adjust for both of these effects. If they didn't, your GPS would be off by about 10 kilometers after just one day. So, we've seen that time isn't a rigid clock. It's flexible. But Einstein himself hinted at something even stranger, something that makes you question the very nature of now. He said the distinction between past, present, and future is just a stubbornly persistent illusion.
This leads us to a wild, fascinating idea called the block universe. The theory goes something like this. If time is just another dimension in space-time, like length or width, what if it's all laid out at once? The past, the present, and the future, all coexisting. In this picture, our sense of time flowing is just our consciousness moving through this already existing four-dimensional block. And that leaves us with one heck of a final question to chew on. Is the future already out there, set in stone, just waiting for us to get there?